Okay. Today what we'll do is we'll start by trying to wrap up, maybe work another problem or two in constrained motion, and then get started on particle kinetics by looking at Newton's second law and then starting to apply that in our different coordinate systems that we have available to us. All right? So I picked a problem out of the book, which we can begin with. Page 106, and I'll try to zoom in a little bit more on that. So what we'll do is we'll neglect the diameter of these small pulleys up here, and here, and here. And what we want to do is determine the relationship between the velocity of A and then the velocity of B. And you can see that I've already written on here distance x for body B defined from this center of this pulley above down to that lower pulley. Okay? Everybody understand the question? So what we'll do is we'll go over here on the board and start working it out now. Okay, so what we want to do is first of all do what in a constrained motion problem with a cable like that?
5 degrees of freedom.
How many degrees of freedom does this system have?
One.
There's one strand of cable in the problem, so 1 degree of freedom. 1 degree of freedom. So what we get, what's our next step? We have 1 degree of freedom.
Label variable segments.
Okay, we labeled the variables. We called one displacement x there, and then we called y is defined also for us in the picture. So then the next step, once we've defined the variables, formula for the length of the cable. Length of the cable. So the length of the cable, how many strands of length x?
2.
Okay, so we have 2 strands of length x. Then we have something different in this problem than we've seen previously. If you come back and look at the problem posed in the book, it looks like there's a diagonal cable length here and then wraps around and doubles up over on the right side. So we have to write that strand, those strands of cable, and so it's not as simple as before where we might have y or something like that. Okay? So how would you expect we're going to get the length of these diagonal strands? Pythagorean relationship relating y and b, defined here in the book, to the length of those cables. So the length that you see across here in the diagonal then looks like it's going to be the square root of y squared plus b squared. Square root of y squared plus b squared. And so over on the right side here where I have the pen sitting, there's 2 of those. And then over on the left, there's one strand. So we end up with, okay, back up here now. We end up with 3 strands that are of length y square plus b square.
Hey, Robert.
Uh-huh.
Why would we not be able just to use y instead of x and just say that that little extra bit is
In the picture, y is defined as from the ceiling up above straight down to where body B sits.
It looks like it's from the center of the pulley.
Yeah, but it goes to the body, I'm sorry, body A. It goes here to body A.
Okay. So you
And
can't just say that
the distance y. B, body B over here, this pulley, I mean, they could have drawn this where it's much lower or much higher. So don't misinterpret the length here for that length right over there.
Okay.
Is that clear? Okay.
I guess it's just a little bit confusing because then we always add the plus C, you know, like because for the constant, so the distance around the pulleys.
Yes.
And why couldn't the plus C just be a little bit bigger?
Well, this what we have to do is we have to define the motion of this body
Oh, okay.
separately from the motion of the body over here.
Okay, because it's going to be
Yeah, they're moved separately, but there is a relationship between their motion.
But those lengths won't stay the same, even though they look the same right now, they won't stay the same once they start moving.
Right. Imagine that this body over here, B, is massive enough to cause this to move downward. If that thing comes on down, that's going to raise this thing up, right, at a certain ratio. And we'll sort of see what that ratio is in a second. Okay? So back to the equation at hand. Then you have some constants, as you mentioned, Julie, around the base of the pulley here. There's always a little piece in there that's not accounted for, unchanging. And then up on these little small pulleys up near the top, there's also a length there that changes. Now, what happens if this body A, let's say it gets way up here high? Doesn't that angle change? Doesn't that angle change? And then that's going to change the constants that we're carrying along. But in the differential sense, what we're looking at is at an instant, in a particular geometric configuration, at an instant of the motion, those are considered second order effects when you start differentiating. So the fact that the tangency, the arc lengths there from the changing tangencies, we can neglect those in typical engineering fashion. Okay. There are applications where that kind of behavior would be critical to take into account, but the analysis would be a lot more complex. Okay. So I think we have a decent relationship over here now. Don't forget to add on those little arc lengths of tangency on the pulleys, and then differentiate this. And I think they ask us to go, what, to the velocities? Yes. To the velocities, so that's our first derivative. So derivative of the constant being 0, we get twice x dot plus 3 times. And then here you want to think of the radical raised to the 1/2 power and apply the power rule to that using implicit differentiation. Because we're differentiating this with respect to time. So what we do is we start with y squared plus b squared to the 1/2, and we differentiate it with respect to the argument inside. And then we differentiate y squared plus b squared with respect to y. And then we differentiate y with respect to t. Chain rule. You've been doing this since first term calculus. Plus the derivative of your constant there is 0. Okay, carrying on with that. We have 2x dot. This is all equal to 0. 2x dot plus 3 times 1/2 of y squared plus b squared to the negative 1/2 times 2y times y dot. Catch me if I make a mistake. Okay. So then what I'd probably do is, what are we trying to do? Find velocity. And actually I failed to write down in the original problem. Normally what I would do is draw a sketch, which I haven't done here. And I would also write down what we're looking for. We're looking for the relationship between
the velocity of A and the velocity of B.
Okay, we want velocity of A as a function of velocity B?
Velocity B is a function of
Okay, so we're looking for the velocity B as the function of velocity A. That's our question. So we want to solve this for the velocity of B, and body B is defined as motion x. So we want to find x dot here. Okay? So if we divide both sides by 2 and then kick this term over to the other side, we're going to have x dot, which is equal to the velocity of b, is going to be equal to then negative 3/4. This radical drops down in the denominator, and I can see something that I failed to reduce earlier. And there's in the numerator a 2y, and then this is the velocity of a right there. And so we can reduce the 2 out, and that should be the answer in the book. Okay, so the velocity of b then is equal to negative 3 times position y times the velocity of a over twice the radical of y squared plus b squared. Does that make sense? Okay. Now what I'd like to do is to draw a little quick sketch of this and sort of take a look at this relationship, because you'll notice this coefficient here is a function of y, position y, the placement of body A. So our picture is looking like this. Here's B, and we've got the pulley mechanism, comes up and over, and then it goes out over here. Doesn't it wrap around underneath and go up over there and come back?
Yeah.
Okay, so it goes up over here, and this is some distance 2b over to this right-hand pulley, and then it wraps around, comes back in, and hooks on here with this body A right there. This being the defined distance y, and this being what we called x earlier, which relates to the speed here. Okay. So let's say that we gave this a positive velocity. V sub A is positive, or greater than 0, motion downward. Physically, you'd observe that you're going to have a negative here. It's going to pull this thing back up for your velocity b. They'll be opposing one another, as expected. There's a 3:2 ratio, but also the ratio here of y. Now, what if y was very large? Imagine the really long cable, and this body A was hanging way, way down there. In other words, the cable strands connected to A would be very close to vertical.
That coefficient's gonna close in on negative, what, 3/2?
Yeah. So what you would observe here is that the B doesn't make much difference if Y is great, right? If Y is great, B doesn't make much difference. And so this radical behaves as if it's just Y, which reduces out. And so in the limit for a large Y, for Y large, the behavior of B appears to be negative 3/2 of the speed of A.
Yeah, and you can see that from the picture too, if you just imagine that they're all vertical.
Yeah, imagine it's vertical, way down there. And so for large Y, then this would be the relationship. So the mechanism, imagine this pulley mechanism was just close together here, and in essence, this thing hanging vertically. You're going to have a 3:2 ratio, a 3:2 ratio in the mechanical advantage there. Does that make sense? Okay. Now, what about the reverse? What about if Y was very, very short relative to this distance B? In other words, we have a wide span here, and we've got a big wide span here, and here is the cable now supporting body A. Very close to being horizontal. And you imagine a motion here.
Well, your coefficient is going to approach negative 3 over 2b.
Y gets really small, going supposed to 0.
Right.
So
If
Oh,
y
then
is
the whole
approaching
thing would just be
zero, then
zero,
we have a
yeah.
condition here, which you might think about mathematically using what? L'Hopital's rule. A condition for very small y, which would be very close to being horizontal like this, then what you might want to do is think about investigating the limit of this as y approaches 0.
Wouldn't that be just 0
Well, you could say in the limit,
Like
isn't it a
0
0 over
to
0 kind of condition?
Well,
It's-
Y is
But you
0,
still have
so
B.
But B
for
is still,
B is still there.
Right.
Ah, yes, thank you. Like that. We don't need L'Hopital's rule. I was just trying to get fancy with it, but unnecessarily so. So as Ian noticed, if y is small, then the velocity of B is going to be approaching negative 3 VA. Well, actually, that goes to 0, doesn't it? I'm sorry. Yeah, just heads towards 0. Okay, over your denominator. So effectively, that heads towards 0 right there. And you deal with the constant in the denominator. And that should make sense to you. Okay, good. So the velocity of B would approach 0 there. Okay, so I just wanted to show you that you have to be a little careful if you start having some geometry involved there, as opposed to these cables just hanging vertically, like you've seen in most of your homework. I think you did have a homework problem that I was challenging you, and hopefully you had a chance to look at that. There's a relationship that exists here between x, and you have a variable changing length here, don't you? And the position of this tractor over here. So in your homework problem, you have to play a little relationship. You have to develop the relationship between your L, x, and x dot would be then the motion of your tractor. How many of you gotten to that problem? One?
I've looked at it. If it
Two of
makes
you?
feel better.
Okay, all right. Okay. And I think that might be adequate on that material. Yeah, I think that's okay for now. No, there's another one I wanted to look at. I went over to the review problems at the end of the chapter, and here's one, and we'll see if my penciling shows up. This one is would trip you up. This one would trip you up without sort of seeing the insight that I'm going to provide you here. What we have here is we have a pair of pulleys rigidly connected to one another. So if one rotates, the other rotates with it up in the top. Okay? We have a single strand of cable. And the key to understanding this problem is that this strand of cable comes up here on this 3-inch radius, and it wraps around here a little bit so that it would allow for this body to move. If this body pulls downward, if body A pulls downward, as they're showing at least through the accelerations here, imagine body A is coming downward, then that's going to cause this pulley arrangement at the top to rotate clockwise, as I've illustrated over here on the left. And while it does that, it's going to unwrap a bit of that cable that's up there, and that becomes part of your length. So what they suggested in the instructions is they said analyze geometrically the consequences of a differential movement of cylinder A. Cylinder A, I think, is what they mean, the top one up here. So here's the differential analysis that I did over here on the side.
Wouldn't cylinder A be the hanging
weight.
cylinder?
Oh, I don't know what it is.
it's the hanging weight.
I think that's what the hanging masses are, is cylinders.
Oh, this cylinder A, yeah,
Right.
okay. And these are our pulleys up here. So imagine, what did they say? Analyze geometrically the consequences of a differential movement of cylinder A. So imagine a consequence of letting cylinder A here drop down a little bit. So if we take the top pulley arrangement and we let it rotate a little bit, dropping this 4-inch radius up here, and that's why I call it delta sub 4, drops it a little bit, then there's a differential displacement downward there. On that 3-inch radius, there's similarly a proportional differential displacement downward there. And the far side over here is going to raise up the differential displacement, I called it delta 4, equal to what you saw over on the right side. So that's the way they suggested doing the analysis. Then here's the trick on following their solution. Down here, if we move to the lower pulley, then this 3-inch displacement right here has to then match the 3-inch drop, or I'm sorry, delta 3 drop right here on this edge. And at the same time that's occurring, the far left edge over here is going to rise up by the amount delta 4. Now the diameter of this lower pulley is 7 inches. And you can see how that lines up above here. So what happens is the center of this lower pulley is where the cylinder B is attached, in the center. And you can see that this displacement profile here is offset a little bit, and the center of that, if you can see that, can you see that? You can't? Not really. Oh, you can't see it?
Yeah.
Okay. Let me just do this quickly up here. Sorry about that. Should have done this in the first place. There's the